So now we know about the basics of probability theory and the distributions of random variables. In this lecture, we're going to talk about long-run averages. What happens if you repeat an experiment lots of times and look at the average value that you get? Like so many things in probability theory, a good way to understand it is again to think about flipping an ordinary coin that has probability 50-50 of coming up heads or tails. So if I flip it just once, the probability of heads is 50%. Well, we already know if I flip it twice, then a quarter of the time I won't get any heads, and half the time I'll get one head, and a quarter of the time I'll get two heads. But what if I flip it lots and lots of times and look at the fraction of heads that I get? You might think as you flip it more and more, the fraction of heads should get closer and closer to a half. And indeed, in this lecture, we'll see that that's so, and we'll understand better how that works. So to start off, let's again imagine flipping a coin twice, and I've graphed here the probabilities for the fraction of heads that you'll get. So a quarter of the time you won't get any heads, half the time you'll get half of them heads, and a quarter of the time you'll get all heads. Simple enough. If we flip three coins, well, we worked out those probabilities before too, and we can see here that there's probability 1/8 of getting no heads, or 3/8 of getting a third heads, 1 out of 3, or 3/8 of getting 2/3 heads, or 2 heads out of 3, and 1/8 probability of getting all heads, 3 out of 3. What if I flip a coin 10 times? So here's a graph when I've flipped 10 coins and looked at the fraction of heads that I get. And we can see from this graph that the most likely fractions are fractions which are close to a half, corresponding to 5 heads out of 10. Now, a little bit less or a little bit more than half heads, corresponding to 4 heads or maybe 6 heads out of 10, are also quite likely. But getting no heads or 1 head or getting 9 heads or 10 heads out of 10 are very unlikely. If we flip even more coins, we can see this more clearly. Here's a graph of the probabilities when we flip 30 coins. And we see now that sure enough, the probabilities closest to the middle, closest to half of the flips being heads, are indeed the highest ones. We can also start to see something else. We can see a little bit about the shape of the graph of these probabilities. We can see that it's highest in the middle, and it falls off to the sides in a nice round shape that might look a bit familiar. If we flip 100 coins, we can look at the graph again. The first thing we see is that all the individual probabilities are getting quite small because there's all different possible results you could get for the fraction of heads when you flip 100 coins. But we can also see the shape, and if we stretch it out, here's another version of the same graph, just stretched out so we can see the probabilities better. And we see, sure enough, we've got this sort of curve shape, which should remind you of the density for the normal distribution that we saw in the last lecture. So what can we say so far? Well, we say that as we flip more and more coins, sure enough, the fraction of heads seems to get closer and closer to being a half, which is what you might expect. But also, if we look at the graph of the probabilities, that is the distribution of the fraction of heads that we get, it looks more and more like it has this curve shape, kind of like the normal distribution. Now, so far you might think, okay, fine, that's true when you flip a coin lots and lots of times, but what about other experiments? Well, let's do another one. So if we remember rolling a 6-sided die, and remember when we roll it and show some side at random, well, we have equal chance of getting any of the numbers 1, 2, 3, 4, 5, or 6, but what if we do it over and over again? So if we just roll one die, then we have equal probabilities of getting any of the numbers 1, 2, 3, 4, 5, or 6. So the graph of the probabilities looks like this, and it's not really very interesting. Well, suppose we roll 3 dice and look at the average of the 3 numbers that appear on the 3 dice. Well, then there's a bunch of possibilities we can get, because each of those dice could have been anything from 1 to 6. But when we look at the averages, these are the probabilities. So right away we can see that the most likely averages when you roll 3 dice are all, well, between about 3 and 4. But it's still possible you might get an average closer to 2 or to 5. It's not very likely you'll get an average near 1 or 6. What if we roll 10 dice? Well, then the probabilities look like this. And now, sure enough, we can start to see some of the old familiar patterns. First of all, we see that the highest probabilities are indeed close to 3.5, or between about 3 and 4, which you may recall, 3.5 was the mean or expected value that we get each time we rolled a die. So if you roll 10, the average of the rolls you'll get will probably be somewhere between about 3 and 4, maybe a little more or a little less. And also we can start to see that same characteristic shape, the bell shape of that normal curve. If you roll 100 dice, then it's even more extreme. It's almost impossible to get anything that's not between 3 and 4 on average. It's got a high peak right near 3.5, and indeed it's got that characteristic shape of the normal distribution. So it wasn't just for flipping coins, it's also for rolling dice. Now, what are the general conclusions that we can make here? Well, the first one is what's called the law of large numbers. It says if you repeat an experiment over and over again and take the average of the results that you get, then that will get closer and closer to the expected value. And as you take an infinite number of repetitions, then you will indeed get the expected value. So if you flip a coin infinitely often, you'll get half heads. And if you roll a die infinitely often, then on average, you will get 3.5. But remember, we also had that characteristic shape. And that's what's called the central limit theorem, and it's extremely important in statistics. And it says that if you repeat an experiment over and over and average up the results, then the distribution of the probabilities for that average will get closer and closer to being normally distributed, or to having the bell-shaped curve. So it says that that normal distribution comes up approximately all over the place whenever we're taking anything that could be viewed as any kind of an average. If you need more convincing, then let's consider another example, this time of an experiment that's highly skewed. Suppose we have an experiment such that each time the outcome is usually 0, but is occasionally 50. And let's say that it's 0 96% of the time, and it's 50 the other 4% of the time. And then we repeat the experiment over and over and look at the probabilities for the average, for x bar. Well, after just one experiment, it's not that interesting. It's almost always 0, and occasionally it's 50. But after 3 experiments, well, it's still usually 0, but occasionally the average takes on some larger values. After 10 experiments, well, we're starting to see different values poke up for this average, but we don't really understand it. After 30 experiments, well, we're starting to see a little more of a pattern. We're starting to see some spread in the probabilities. After 100 repetitions of the experiment, we can start to see that most of the probabilities are pretty close to 0, but they're starting to spread out in a sort of a shape. And if we see that graph again just spread out a little more so we can look at it better, we see sure enough, after 100 experiments of this very, very skewed example, we still see this characteristic curve starting to appear of the bell shape, or the normal distribution. In this case, it's centered around the value 2 because the mean value in that funny skewed experiment was indeed equal to 4% multiplied by 50, which is 2. A whole different way to think about the central limit theorem is through a graphical display called a quincunx, which is shown here. It shows balls that are falling from above and hitting against these knobs or nails and bouncing around. And each time a ball hits a nail, it might bounce a bit to the left or it might bounce a bit to the right. But we can see that each time that adds a certain random amount to the position of the ball, whether it moves a bit left or a bit right. And after it gets through all the nails, well, its final position is kind of represented as a sum or some sort of average of all these different influences on it. And so as we run this for a long time, and as we keep track of where the different balls have landed, at first it seems like they could land all over the place, but after a while, sure enough, the distribution of where they land starts to approximately look like that normal distribution, or that bell shape again. Now, these results can be understood a little bit better if we remember what we learned about the mean and variance of probability distributions in previous lectures. So if we imagine that we're repeating a bunch of experiments, and the results of the experiments can be written as x1, x2, x3, and so on, and suppose we know that the mean or expected value of each of the experiments is some number, let's call it m, and suppose we know that the variance of each of those experiments is some other number, let's call it v, then if we look at the average, so if we let x bar be the average of x1, x2 up to xn, then, well, the expected value of x bar of the average, as you'd expect, is just the same as m. It's the same on average. If it's like the average of the average is the same of the averages, if you want to think of it that way. But what about the variance? That's a little more interesting. So the variance of x bar, well, if you remember your properties of variance, since we're repeating these experiments independently, then the variance of that sum is just the sum of the variances, so it's n times v. But then we had the variance of that sum divided by n. But remember, with variance, if you multiply by a constant, or if you divide by a constant, then the variance is affected by the square. So actually we take that n times v and divide it by n squared. And it means we get a variance which is equal to v over n. And why is that important? Well, it's important because it's going to 0 as n goes to infinity. It means if you repeat the experiment more and more, then the variance, or the uncertainty, will go to 0. So also the standard deviation, which is the square root of the variance, will go to 0. So it means as you repeat an experiment over and over and take averages, then the amount of uncertainty gets less and less, and we get more and more certain of where we are. So this is a very important property of repeating experiments over and over again. As a final note, I want to mention that the central limit theorem provides an explanation for that empirical rule that Allison taught us about earlier. Remember that she said, well, with the empirical rule, it seems that with a lot of data, it has this neat property that about 68% of it is within one standard deviation of the mean, and about 95% of it is within two standard deviations of the mean, and about 99.7% of it is within 3 standard deviations of the mean. Before, that might have sounded just like magic, and when we saw that our data approximately followed that, it seemed amazing. But now that we know the central limit theorem, we can say, aha, these are the probabilities which approximately correspond to a normal distribution. So if we go back to that graph of a normal distribution, then we can say, well, what fraction of the area underneath the curve is indeed within one standard deviation, and sure enough, that area is about equal to 68%. If we look at the area which is within 2 standard deviations of the mean, sure enough, it's about 95%. And if we look at the area under the curve that's within 3 standard deviations of the mean, sure enough, it's about 99.7% of all the area under the graph. So when someone says, hey, this data follows the empirical rule, they're really telling you, hey, this data follows the normal distribution. And we're not so surprised anymore because we see, because of the central limit theorem, lots and lots of data follows the normal distribution, at least approximately. Now, not all data, and we've already seen examples of data which are skewed or have some other funny distribution, and in that case, they might not follow the central limit theorem. We'll see more about that as we go on. But in lots of cases, anything that arises from some sort of an average or some sort of lots of different little influences will tend to approximately follow the normal distribution. And we'll see as we go on that that allows us to make all sorts of inferences in statistics.